This recording for Unit 3, Chapter 7 on Energy for the problems continued. Problem 9. Consider the inelastic collision between the two freight cars in the previous chapter. The momentum before and after the collision is the same. The kinetic energy, however, is less after the collision than before the collision. How much less, and what becomes of this energy? The last question we can answer right away, since it's an inelastic collision. Inelastic collision. That loss in kinetic energy, however much that is, loss of kinetic energy becomes heat as the two are colliding. That energy is dissipated as heat and damage between the two. Okay, let's look at the calculations. We would have to know what the mass is of the two. However, we can even do it without. Kinetic energy equals 1/2 mass times velocity squared, and then that's 1/2 times mass times 10 squared. So that would be whatever the mass is, as I said. 50, 1/2 times 100 is 50 times the mass. Versus when the two have collided, we have kinetic energy equals 1/2 the mass times velocity squared, which in this case is 5 squared. Notice that I left a little bit of a gap there because the two have collided, so the two are together, one in the same system, so we have twice the mass. That's why I left a little gap there. So 1/2 times 2m times 5 squared. We come up with 1/2 times 2 is 1 times 5 squared is 25, and we still have the mass, so m. So we can see that half the energy, half the kinetic energy is gone. If we had attached some kind of mass here, we could have written as follows. We could have said, okay, how about if m equals 10,000 kilograms? Well, then in the first one we would have 50 times 10,000 kilograms is 500,000. And here, if we have meters per second, we could also write joules for the energy. And the second time around, we have 25 times 10,000, which is 250,000 joules. So either way, if we use the mass or if we don't, we come up with that either way 50% of the kinetic energy is lost and dissipated as heat. Problem 11. How many kilometers per liter will a car obtain if its engine is 25% efficient and it encounters an average retarding force of 500 newtons at highway speed? Assume that the energy content of gasoline is 40 megajoules per liter. So when I look at these numbers here, I'm going to come up with that combining these here, then 10 megajoules per liter is actually used for the kinetic energy of the car, while the remaining 30 megajoules per liter is wasted as heat. That's exactly what the efficiency means. Wasted as heat, not off heat. There we go. Okay, let's see how we calculate that. Well, we know that the kinetic energy is 10 megajoules for every liter. I'm just going to leave the liter out of here because at the end it's going to say anyway how many kilometers we're going to make for that 1 liter. So it's going to be 10 megajoules per that liter, and that now is being used up by the frictional force that goes into the work, so frictional force times the distance, and these two here are to be set equal, because set equal because the kinetic energy of 10 megajoules is used up by the friction, and of course we could say, well, we're putting that energy into the car, but then we would increase the kinetic energy of the car to 10 megajoules, and the car would be really, really fast, but instead it's simply used up by the work due to friction, and the speed of the car actually stays the same. I just set here highway speed of 100 kilometers per hour. Okay, so here we also have 10 megajoules, and we have a frictional force of 500 newtons times the distance that we're supposed to figure out. Well, we divide the two, so distance equals 10 million divided by 500, which comes out to 20,000. 20,000, and we're in base units, so joules divided by newtons is meters. Remember that the joule is also newton meter, and that of course is 20 kilometers. 20 kilometers is 12.5 miles. A liter is about a quarter gallon, so we would say, okay, what if the same car here takes on a gallon? Then we would have to multiply our answer by 4. 4 times 12.5 is 50 miles, so per gallon we would get 50 miles, so that's a pretty fuel efficient car. Problem 12. The power we derive from metabolism can do work and can generate heat. A. What is the mechanical efficiency of a relatively inactive person who expends 100 watts of power, so expends 100 watts of power to produce about 1 watt of power in the form of work Again, the first W here means watt, while generating about 99 watts of heat. Well, when you look at the numbers, you come up with 1% efficiency. Part A. Part B. What is the mechanical efficiency of a cyclist who, in a burst of effort, produces 100 watts of mechanical power from 1000 watt of metabolic power? So expends 1000 watts to produce 100 watts, and that of course is a 10% efficiency.